Okay, Spectre, please get us underway.
Okay. Well, so hello, everybody. Good afternoon. And I have the pleasure to chair the last session of the data analysis. I'm Shweta Shah from Hanover in Germany, with all the fires blazing around me. So not to affect our Earth with more adverse effects of climate change, we are organizing the entire LISA Symposium online. And yeah, so let's begin the session. We've got Muratore from Italia. She's a former pupil of Stefano Vitale, and she will tell us about the null channels of TDI. So Martina, the floor is yours.
Thank you so much for the invitation, and thank you for giving me the opportunity to present my work. So I will share the screen. Okay. So I'm going to speak about the effectiveness of the new channel as instrument noise monitors for LISA. I want to underline that this work has been done in collaboration also with Olaf Hartwig, Daniele Vetugno, Stefano Vitale, and Willa Joseph Weber. I just want to really give you a quick recap about what has been done, what has been said so far. So we know that LISA is dominated by the laser frequency noise, and Jean-Baptiste nicely introduced us this topic on the 26th. Just to show you what I mean, here I reported a PSD, and you can actually see that the noise of, in case we don't do any kind of laser noise reduction, the level of the raw data are the one that I reported here in red. Then if you're able to apply this post-processing technique called time-delay interferometry, we are then able to reduce the level of the noise lower than the so-called requirement that are the one that I reported in black. After this, we have to apply other pipeline, this so-called initial noise reduction pipeline. And this one actually helps us to reduce other sources of noise, like the clock noise, the tilt to length, or the spacecraft drifter. And we will see a talk regarding that by Olaf Hartwig. And then we also, you should also have seen many talks on the LISA instrumentation section on the 26th. What I would like to say is that, so at the end, we are going to be left just with two main sources of noise, that are the acceleration noise and the optical metrology noise. And I will focus on these two kinds of sources of noise for my talk. So to have an idea, this is actually the kind of secondary noise that we see in the so-called time delay interferometry X, that is the standard TDI channel used for detect gravitational waves. So if you look again at this PSD versus frequency, what you can notice here is that at the high frequency, you're actually dominated by the optical metrology noise. That is the blue data here, where I superimpose the analytical model. Instead, the low frequency for this TDI, you're actually dominated by the acceleration noise. I did the simulation running the LISA instrument. That is one of the two that we use in our LISA community. And this is the level of the acceleration, the optical metrology noise that we actually are currently using for the as a requirement. So why I'm showing that, just to introduce the topic that is actually important for us to need to know the instrumental noise. Why we care so much in doing this research and these studies. So in general, in case we are looking for sources with high SNR, actually knowing or not having a good knowledge of the noise doesn't make such a big difference. Different is the case when we are looking for sources like the stochastic gravitational wave background, because as you saw by the talk on Nichols kinesis yesterday, we can just give a simple example reporting the standard characteristic string for LISA here. So in case we just in case we just want to have our data, we actually just apply the PSD of our data. What we're actually going to have, if we just consider the galactic background, ignoring all the other sources, this is actually the level of the data of your PSD that you're going to have. So you're going to have this kind of bump in this frequency. Instead, in case you will just have noise without any kind of signal, the kind of sensitivity that you're going to have is actually this green one. So what the point I want to make here is that if you would like actually to try to be able to understand the difference between the presence of a galactic background and on your noise, you have to be able to somehow try to disentangle what is the noise from your stochastic gravitational wave background. Unfortunately, for LISA, we cannot apply a technique like cross correlation. That is the standard technique that have been using for LIGO, and Virgo. So we have to try to use a different way to characterize our noise. So there are actually two possibilities to characterize our noise. One is the so-called pre-flight modeling. So we can try to characterize the noise by pre-flight estimation and modeling and campaign. Otherwise, you can actually try to look for particular TDI combinations that are called new channels. And these combinations are characterized by suppressing the gravitational wave signals, but they still carry some information on the noise. So regarding the first point, I just want to quickly report what has already been said. So if we actually try to do an in-flight estimate on pre-flight estimation of our noise, what happened? So the main problem is that we are not sure that we are able actually to model and predict very accurately what is going to be our model once LISA will fly. An example we can just see here, where I just take this image from the talk of Daniele Vetrugno, where we actually compare the model of the LISA pathfinder that we have, and actually the kind of noise that we are able now, that we have knowledge at the moment. So as you can see here, there is part of the noise that is actually still not understood. This is actually just show you how difficult it is actually to try to predict very accurately what is going to be the model, what is going to be the noise in flight for LISA. In addition, we have also to underline that we cannot, unfortunately, do all the possible kinds of testing on ground for LISA, because there is some part that actually cannot be tested. For example, the longer if interferometry, we cannot do an end-to-end testing. Having said that, one of the possibilities then is to try to use these new channels. And here I just reported a sensitivity plot that compare the different sensitivity of different TDI combinations. So regarding what is the meaning of this different TDI combination, again, I invite you to look at the Jean-Baptiste talk that nicely explain the different TDI combination. And again, how we can relate this different TDI combination. There is going to be a talk by Mauro Pieroni, so I'm not going to enter into detail. Here, I just want to show in particular these two curves. So one is the standard TDI-X. As you can see, it's the more sensitive to gravitational waves. Instead, the so-called null channel that I would like to use is this one, it is the TDI-zeta. And you can see that it's much less sensitive to gravitational wave compared to X. So having said that, if we then try to estimate how actually our noise will propagate in the TDI-zeta, I reported here, again, the PSD, considering the optical metrology noise, that is the blue one, against the acceleration noise. So what you can see, if you actually compare the new estimation of the noise compared to the zeta, to the X channel, unfortunately, the zeta channel is totally estimated by the readout noise. Instead, the X channel, we see that is dominated by the acceleration noise at low frequency, but it also dominated by the OMS noise at high frequency. So from this comparing the two plot, it actually looks like that you can use the zeta channel to try to estimate the noise of the X channel at high frequency. If you want to understand why there is this difference in behavior, we can just quickly look at these two formula, in particular how the noise propagates in TDI zeta. And we can actually see that the reason why in TDI zeta we don't see acceleration noise at low frequency is that because there is this factor that actually, let's say, reduce the acceleration noise at low frequency. And this is why the TDI zeta is dominated mostly by OMS noise. So again, so what, having said that, we would like then to try to see what we can do using this new channel to try to do a kind of in-flight estimation of our noise. So just to give you an idea about what order of the optical metrology noise we should have in the TDI zeta in order to be able to estimate also the acceleration noise in this channel, we actually computed that in order to zeta to be also dominated by acceleration noise at low frequency, like the TDI-X, we will need an OMS noise of this level. And you can see that there are many order of magnitude between the OMS noise that is required at the moment for LISA and the idealistic one that we would like to achieve. So it actually means that unfortunately we cannot do, at the moment it looks like that it's very unlikely that the TDI zeta can estimate the acceleration noise at low frequency. So what the proposed solution that we then try to do is to try to suggest a different approach at the problem, and so try to avoid to use, for example, many approximation, many assumptions that people were doing so far in order to try to use this new channel in order to try to estimate the stochastic background, assuming the knowledge of the noise. So what we try to do is to try to compute a formula that does not arrive of any assumption of the actual noise level of the test mass and the optical metrology noise. And we also we find it out that there is a way to combine the data that they are actually independent from time, and they also are robust against no stationarity. Unfortunately, the problem of this is that we also stay in the same assumption that the noise are not correlated, because as I will explain to you later on, is that we cannot use any new channel to try to estimate uncorrelated noise. So in order to try to find this, to try to understand how zeta can actually estimate our noise in the X channel, we need to look for a function f, such that we are able to find an upper limit using the zeta channel. So upper limit means that we have to find a function that applies to our noise in zeta is actually bigger than the noise in X. This will tell us that for sure we are able to find an upper bound on the X noise. Just to show you what do I mean for S zeta Sx, we can just write it down simply the noise of these two channels, where S zeta is just made up of the sum of the acceleration noise multiplied by its transfer function, plus the sum of the optical metrology noise multiplied by its transfer function, and the same for zeta. So if you do some calculation, you're actually able to find this function that has the following value. I'm not going into detail of all the calculation, but in case you are interested, you can just have a look of this paper, the paper that we published and put in archive, but we are going to have an updated version in mostly 1 week. So just to do this overall presentation, so if you just look at the total noise in X, that is the green one, for our estimation, we saw that actually we are able to estimate the noise in the TDI X using the zeta channel by this far amount. So actually using zeta to estimate X tell you that this is actually the noise that you are going to get. Just to have an idea, you can actually do the ratio between these two estimation. You actually see that at low frequency, your estimation of the noise in X is a little bit above by the actual value of the noise in X. Instead, you are a little bit better, obviously, at high frequency, where your level is lower than 2 by between 30 milliamps and 100 milliamps. And this is actually expected because, as I showed you before, both the combination dominated by OMS noise at high frequency. So it's actually the probability that you can use zeta is better at high frequency than at low frequency. Here, I just want to show you very quickly why we cannot use the null channel to estimate correlated noise. So if you just write the intermediary variable, and Jean-Baptiste already on Monday already explained how you can build this variable. In our case, we build them using the optical metrology noise and the test mass acceleration noise. If you then actually use this eta to build your zeta channel, and here I reported the standard case of equal arm length, you can actually see that how these eta variable are combined. So for example, if we just take this eta 31 and eta 32, and you actually look at the plot on the right, you see that every noise that is common between these two optical bench or these two MOSA will directly cancel out. So this actually means that any new channel, for the way that they're built, actually cannot be used for doing any kind of estimation of correlated noise in the sensitive channels. So having said that, I would like to show you to conclude, showing how you can actually use this estimation of the upper bound of the noise to try to estimate the stochastic background, more than estimate, to try to give an upper bound on the stochastic background that we are able to see with LISA. So the first thing that you can actually compute is actually that using is an obvious estimation. So if you just take the TDI X, that is, if you just take the data that you receive with the stochastic background, you can just plot like a sensitivity, a curve, and you are sure that your stochastic background will never be bigger than what we actually observe. The second thing that you can estimate is the so-called detection threshold. And it means that using the zeta channel, you can actually say that this is the detection that I can estimate, and it means that in order to be able to distinguish the noise from the stochastic background, I need that my stochastic background is up to this curve. So if you really in reality, obviously, we cannot represent just the noise as I represented here, but what we can actually define is an upper bound, consider the realistic measurement that we will have. So in case of the TDI-X, you will that's what you are going to estimate. You can say that your estimate is going to be bigger, obviously, than hypothetic model on the stochastic gravitational wave background. So this computation rule out possible model that you actually are not seeing in your data. Instead, regarding the lower bound, what you can actually have, you can actually see that you are able to detect and distinguish your stochastic background if the difference between what you measure in X minus the new zeta channel that we estimate divided by the different transfer function is actually smaller than your stochastic background. So if the stochastic background is bigger than this value, that means it's upper this line, it means that you're actually able to distinguish the noise and the signals. So just for conclude, what we did, we actually did an estimation. We actually tried to understand how we can use the null channel to see how different noise enter in X. And what we saw is that we are actually able to estimate the noise better between 30 and 1 milliards because our estimate was up by a factor of 4 in power. And actually also there is, I don't want to give a very sad message, let's say, because the kind of detection threshold that we find actually told us that we are able to detect and distinguish between the noise if we have a big stochastic background. And actually that can also be helpful for us to rule out different models on the stochastic background. And in general, as I told you, we unfortunately cannot use the null channel to do any kind of estimation on correlated noise. And I see that I'm already out of time, so I will stop here, and this is mostly my conclusion. Thank you.
Thanks, Martina, and thanks for reminding us that we actually cannot use cross correlation for Lisa, unlike LIGO. It sounds trivial sometimes, but most people forget, and by people I mean me. Okay, so we have a bunch of questions. I will be greedy and ask my own trivial question. Which for the zeta, which gravitational wave source did you use?
We were considering a very simplified, let's say, stochastic background means that we are considering sources equally distributed along the sky, very simple sources. If you use many of them, they form a kind of stochastic background because they come from different parts of this equally distributed for different points on the sky. And we also check our analytical computation with the GV response that was as you know, coded by Jean-Baptiste.
Mm-hmm. Okay, so I see a hand up. Quentin, go ahead and ask your question.
Yes, hi, Martina. Thank you for for your talk. It's very interesting. So, of course, your job is to be pessimistic, right? Or at least to warn the unconscious data analysts that want to extract the stochastic backgrounds from the noise. I had a similar question as Sweta actually about the impact of the shape of the stochastic background you're considering, because you showed to us these upper limits of detection, but of course you have to take into account the integration, the integrated signal to noise ratio over the whole frequency band. So how do you take that into account, and which shapes are you considering?
Okay, so let's see if I understand the question. So on the right is the transfer function response. So the first one, so I actually really compute this formula. So for I do the difference between the noise. So in this case, sorry, let me see here. So this is really the noise of the instrument. So I cannot obviously do that because I don't consider I don't have data. Okay, so this is actually what we have, and this is actually what I was using. So this is really the noise of the instrument. So if you use Lisa instrument, you just say turn on the optical metrology and the test mass acceleration noise. I multiply by this f, the zeta, and the f is actually the one that I show you. And then I divide it by these two transfer function. And this transfer function, the first one is the transfer function of x towards a general stochastic background, isotropic. So I'm not considering any particular shape. I consider time like agnostic from the kind of stochastic background I'm looking for. So it's not a deterministic signal. That is what you were wondering, or
okay, so you mean
I mean I do the integration along all the frequency, along also all the direction.
Okay, and you assume it's white or constant PSD? Okay.
Yes, it's like white. It's actually white. Like the PSD is kind of one, like so, like a white constant, like a white noise. It's like a white noise.
Okay, understood. Thank you.
Okay.
Okay, so there's a couple of more questions. One is a yes/no question from Jean-Baptiste. What are you interested in a noise? What? No, why? Come on, Jean-Baptiste, get your English right. Why are you interested in a noise upper bound?
Okay, so you mean this red line? I'm interested in this because it actually tells us it's a confidence level, because this noise upper bound is fixed. So it's not like floating up and forth if you have a signal, and it's something that you can actually estimate. So this is actually the data that we are going to have. And we know that we can use this upper bound, and we know that if we look, if for example, you take your instrument, you compute the PSD, and the PSD is more than this upper bound, you can say this is a stochastic signal, because it's actually the threshold that tell you this is a gravitational wave, this is not a gravitational wave. Obviously, it's not exactly this, because again, here just consider the noise here, not the signal. But you know that you can do this formula with your real data, and you know that if you, for example, you have X, and your X is bigger than this for you know this is a stochastic background. I don't know if I answered these questions.
That made sense to me. So we're already at time, but there's just one more question from Jean-Baptiste. I'll just read it, it's long. So when studying SGWB, how can you tell if an excess of power in X is due to the SGWB or another source of noise that we didn't consider? One, do you think there are other combinations that can constrain other sources' noise or discriminate easily between signal and noise?
Okay, so regarding the first question, I actually didn't read the last point. So we did this study just considering test mass acceleration noise and optical metrology noise. So we know from this upper bound that whatever is upper to this is a stochastic background. What we should do will be actually to include other kind of sources of noise, like the tilt to length and so on, to see if actually they give you a different upper bound and something like that. So that's the main that's the main point that I cannot tell sure with just this noise that what we're going to see is a stochastic background, because I need to recompute including other noise. And regarding different signals, is a stochastic background or not? I think this is not our job, meaning that so we are going to run a global fit, I suppose. And so for the other noise sources, I think they are going to have template to fit them. So the idea is that if you are able to fit also all sorts of all the other sources that you know, the leftover should be a stochastic background. And in order to know if it's a noise or if it's a stochastic background, you need to work by threshold.
All right, so thanks, Martina, for that talk. We will
Thank
move on to the next one. We are already 2 minutes after. So our next speaker is Olaf Hartwig. He is my former colleague from AEI, and he's now stationed in Sirte Theory Group in Paris Observatory. And he will tell us about the unimportance of clock synchronization for a certain frequency band in TDI. So Olaf, go ahead, please.
Yes, hello. Thanks for the introduction. Let me try to share my presentation. It works. Can you see my slides?
Yes.
Okay, perfect. Yes, so Shweta announced that we'll be speaking about time-delay interferometry without clock synchronization. This is present the results from a paper that I've been working on together with Jean-Baptiste, who's now at Glasgow, and Martin, who is also at the AI, and 3 colleagues from the CIRT, the Oriens, Marc, Lily, and Peter Wolf. And just a very short recap, we already heard a lot about TDI, so I will keep the introduction super short. As you probably know, TDI is part of the 0 to L1 pipeline, which takes as input 0.5 data, which is just the reformatted telemetered data, together with ground-based observation data like orbit spacecraft position tracking, and processes this data it gets processed by this pipeline to get L1 data, which are the TDI time series you use as input for the data analysis, and all the additional information you need, like clock desynchronizations and so on. And TDI is the arguably most important step of this pipeline, which reduces laser noise by many orders of magnitude. Now, as I said, we already heard a lot about TDI, but I want to remind of 2 important aspects for how it works, because that's the foundation for this work. And for this, it's useful to think of a simplified laser link, so not of the whole spacecraft, but just of the main components, which are in each spacecraft. You have a laser. This laser has some laser noise time series, just indicated by this little cartoon up here. And the laser of this spacecraft will be transmitted to the distant spacecraft and interfered there with a local laser on that spacecraft. The whole setup is pretty much symmetric. And this laser has its own laser frequency noise, such that the signal that we record on board the other spacecraft is simply the difference between the 2 laser frequency noise time series. where one of them arrives with a delay by the light travel time between the spacecrafts. We usually write that using such a delay operator. And to get an intuitive understanding of what's happening here, it's useful to look at a space-time diagram, where this is the world line of spacecraft 1, this is the world line of spacecraft 2. So the measurement that you record here will contain laser noise of that spacecraft at the time of reception, minus laser noise of a distant spacecraft at the corresponding time of emission. So that is what this delay operator does. It relates this time to this time. And of course, this laser link on its own, it will be completely dominated by laser frequency noise, but this goes away if you construct full TDI combinations, which look a bit like this. So this is the space-time diagram of the first generation max-next combination, where you see that two beams are combined that were emitted from the same spacecraft at the same event. And you build this combination by simply combining measurements at the correct times, such that always one of these two noise terms that we had in our measurement cancels. And this is not a new idea. If you want to know about this specific interpretation of TDI in form of geometric photon paths, here are two references that explain that in a lot of detail. Now, my talk is about TDI with desynchronized blocks. So we try to understand how you can apply this algorithm. If you also take into account that each spacecraft has its own individual clock. And for this, it's useful to quickly recap what are the different timescales that you might encounter in LISA. One of them is the TCB time t, which is defined as the time shown of a perfect clock sitting at the solar system barycenter. That's a global timescale, and that's usually the one used for data analysis and for the standard literature version of TDI. We have the proper times of the three spacecrafts, which are the times shown of a perfect clock sitting in spacecraft I. They are related to the TCB time by general relativity, and they are very useful for describing the local physics inside one spacecraft. And finally, we have the actual onboard clock times for each spacecraft, which are the times shown by the actual physical clocks that are running in the spacecraft. Each spacecraft is equipped with an ultra-stable oscillator with a clock. And this clock gives you some timing signals, and these are the times that we can actually measure on the spacecraft. These are the only times that we can actually measure on the spacecraft, because all of these time frames up here are idealized times. And these differ from the proper times by instrumental imperfections of the clock. Now, to understand how you can do TDI, even if your data is given according to the spacecraft clocks, again, it's useful to look at the space-time diagram. Here, I will first walk you through a very basic TDI combination using data that is given in the TCB. So you start by combining two measurements at the same time, some TCB time TA. And as I mentioned before, you have to add to that measurements on the spacecraft 3 and spacecraft 2, the other two spacecraft, that are shifted by the correct amount, such that one of the laser noise terms, the one of the spacecraft 3 in this case, cancels out when you combine these two. And the time shift that you need to apply in this case, if everything is given in the TCB, is simply the light travel time, which you can compute from your estimates of the spacecraft positions together with the onboard measurements. And what you then get, if you form such a combination, is a virtual interferometer where two beams were emitted from the same spacecraft with a small time delay, such that the very typical formula for laser frequency noise applies. If this time delay is small, this looks like a derivative, and you simply get the phase noise becomes frequency noise, and it gets scaled by the time difference. This is not a TDI combination, it's a standard Michelson, but for a proper TDI combination, this is a very small number. Now, if you want to do the same thing using clock times, you can actually write down exactly the same space-time diagram. You again start with measurements given at some arbitrary starting time. But this time, these measurements are given according to the clock time, which are right here. Now, for laser noise to cancel, you need to add to those measurements recorded on the other two spacecraft, time shifted by the correct amount. That again, the laser noise of the beam that was received here and the laser gun of the beam that is emitted here cancel out. And the time shift between these two times that you need to apply is now a pseudo range, which is something that we can actually measure directly on the spacecraft, because it is simply the difference between the clock time spacecraft 1 at emission, at reception, and the clock time of the other spacecraft at emission. Oh, there's a typo here. It should be tau 3 hat. Sorry about that. And physically, this corresponds to exactly the same interferometer. The only difference is that all the times are now given according to the spacecraft clock 1. But the crucial point is that if this number is very small, picoseconds in the TCB, then it will also be very small expressed according to the real clocks. So laser noise will still be strongly suppressed in these variables. Now, this was the general idea, how it works. And now I want to speak a little bit about some technical details, how you can actually do that in practice and why it's beneficial to work directly in the clock time frames. And for this, first want to quickly recap how LISA actually measures the phase, what we actually measure. And as you probably know, LISA uses heterodynamic interferometry, which means that we interfere beams at not exactly the same frequency, but with the 5 to 25 megahertz offset, such that the beat note signal that we get is a quickly oscillating beat note. And the gravitational wave signal is then encoded in the phase of the beat note, which is recovered from the phase meter, which is driven by a clock. I posted here a little graph of how these beat notes evolve over time. As you see, they are almost constant. They evolve very smoothly. And you also, on the scale of megahertz, you don't see any fluctuations in them. For this, you need to zoom in. So here I have another plot where I subtracted large trends from these beat notes. And you can see that they fluctuate by up to 100 hertz. This is laser frequency noise that we need to get rid of. And once we do get rid of this laser frequency noise, the gravitational wave will be encoded as a microcycle phase fluctuation, which in terms of frequency corresponds to about 100 nanohertz. One thing that's important is that laser frequency noise is not the only noise source in there, but one that is also quite significant is clock noise due to these local clocks. The reason that is that, as I said, we have heterodynamic signals up to 25 megahertz. They're oscillating very quickly. And to determine the phase, we need to compare them to a local reference clock. We do that in practice by digitizing the signal and then using a digital phasewidth loop. But the technical implementation actually doesn't matter. You always have to compare this oscillating signal to some reference clock. And if you want to reach microcycle precision in this comparison, it turns out that your clock needs to be stable to 40 femtosecond per square root hertz. And that is it's a much too stringent requirement for existing space qualified clocks. Such clocks simply don't exist at the moment. And one little detail that's important is that if you work directly with these large 25 megahertz beat notes, any time shift that you apply to them will also inherit that same timing requirement, because anytime you apply a time shift to your time series, you get the same kind of phase noise coupling. Just to give you an idea of how far away we are, here's a plot with some data from a clock measured by CNES. That's an ultra-stable oscillator, a quartz oscillator that will fly on the Power mission. It's not the atomic clock, it's a quartz oscillator. And as you can see, it's about 2 to 3 orders of magnitude above the requirement in the worst case. Now, that's a bit, so what can we do about that? The solution is to measure the clock noise and suppress it in the post-processing. And the way we do that is by using modulations of the clock onto the laser beam. So we have 2 of them. One of them is a so-called pseudo-random number code, which is just the sequences of ones and zeros, which is modulated as a phase modulation to the beam. So it is a code that looks like this. And the second one is a high frequency modulation at 2.4 gigahertz. If you modulate a laser beam with such a sinusoidal signal, you get sidebands, upper and lower sidebands, which are indicated here. So instead of having just a carrier beam, you in effect have 2 more beams that you can use. And the whole setup is symmetric. So you have a 2.4 gigahertz sideband on spacecraft 1, and you have a sideband at a slightly different frequency on spacecraft 2. And same as before, the spacecraft exchange their beams along the interspacecraft interferometer, they interfere, and you then get not just 1 beat node, but you get 3 beat nodes, 1 for the carriers and 1 for the 2 sidebands. And in addition, you also get the superposition of these 2 PRN codes, which you can then time shift against each other to determine the absolute range. And but it's important to point out that both of these signals, this clock signal and this PRN signal, in principle measure the same quantity. They measure the pseudo range because they are signals derived from the local clock. So in this beat node, the phase fluctuation in this beat node tell you about the relationship of this clock when it was emitted and the relationship of this clock when it was received. And this allows us to measure the pseudo range at a very high precision. What does very high mean? Here's a kind of plot where I show 2 more measurements provided by Michael Born and Kohei Yamamoto from AI. One of them is for the performance of the EOM and fiber amplifier used in the laser prototype, and you can see that it is mostly within the requirement. It slightly violates it, at least this measurement still at the most critical frequency. And there are 2 reasons for that. One of them is just it's very challenging to get it below that, from what I understood. And the second one is that this requirement that I put here is very stringent at this frequency. So the requirement can be is relaxed a bit in the latest version. And I don't know if I think the laser also performs a little bit better, so we are okay for that. But it is a critical noise source. Whereas this divider here measured by Kohei is part of the electrical conversion chain. These different frequencies that we generate, they all need to, there's a long chain of conversions, but those are not dominant and they're subdominant with respect to the UM5 amplifier. But the summary is that these measurements together allow you to measure the pseudo range that we need for our version of TDI at the required level. And to summarize what we plan to do with that, so we propose a relatively simple pipeline where you start with your 0.5 data. You do some relatively simple ranging processing in which you combine the PRN code and the sideband to get a very high precision and accurate readout of the pseudo range. You then use that to compute your TDI combinations. And since our pseudo range is so precise, we can do that directly on the megahertz speed node and will cancel laser and clock noise in the same step. And what you then get are noise-free variables that you simply still have to time shift to the correct reference frame, but the required precision for that is much lower than for the full variable. This is in contrast to the standard pipeline, if you want, which has some more steps, because previously the idea how to do that was to first do the frame conversion and clock synchronization, to first put everything in the TCB, then remove laser noise. And in order to reach the required precision to do that, you have to remove megahertz phase ramps beforehand, which then implies that you also have to do an extra clock noise correction step. And I think I'm starting to run out of time, so I also started a bit late. But here's just one plot where we show simulation results that this actually works. So we tested that numerically using time domain simulations with realistic orbits, realistic clock noise, different clock offsets, laser noise, sandband noise, and PRN noise. And we also included the secondary noises. And you can see that we reach exactly the same performance as you would without any of these extra noise sources. So the dotted line here shows the model accounting just for the secondary noises and agrees perfectly with our fully processed result. And we also had a simulation where we turned off the secondary noises, and we see that we end up at the level limited by this previously mentioned modulation noise, which is also perfectly in agreement with previous results. So this pipeline really performs exactly the same. It's just simpler to implement. Yes, this brings me to my conclusion. The main point is that you can construct TDI variables directly from unsynchronized data, that the necessary delays can be extracted from the onboard ranging measurement at the required precision, and this simplifies the pipeline. The resulting TDI variables still need to be synchronized to TCB, but at a much lower precision. And the second remark is that this version of suppressing clock noise by time shifting total frequencies was actually also experimentally demonstrated in the hexagon experiment that Kohei told us about in a previous session. And that's all I have. Thanks for your attention.
So thanks, Olaf. I must compliment on your view, the view graphs. They just keep getting better and better every time.
Thank you.
Okay, so I'll be greedy again and ask my own question. So what does this PHARAO stand for?
FARAO?
You know, the real clock. Yeah, the PHARAO.
Oh, I don't know. It's a French acronym, I think. It's a part of the atomic clock ensemble in space. It's an atomic clock that they want to put on the International Space Station, but I don't know what it stands for.
Okay, and actually I had this question about, these are noise curves that are measurement of actual real clocks that are used in simulation, and then you run data analysis on it. And you know, we have this plan, right, to use the real clock data from Hexagon into the data analysis. Don't you think it's a little bit going around the circle, repeating the same thing? this already maybe satisfies the study to conclude which clock to use, because the PSDs of these are actually measurement from real clocks. So what's the added advantage of using real clock in INREP, for example?
I think
it somehow feels to me like this dog chasing its own tail.
No, I think it's not quite the same thing, because the measurement that I show here, it's a measured PSD of the very good space modified USO, but I think the clocks that they actually have in the hexagon, they're not as good. They're less good. But I didn't take the actual time series of the clock. I got a measurement of the PSD and I generate my own perfect Gaussian noise that has the same PSD, but it doesn't have any glitches, it doesn't have any artifacts. So there's a lot of idealizations in the simulation that you don't have in real experiment.
All right, well, so there's no hands raised. There was one question I see from Alistair. Be interested to know more about the prototype laser in the plot. Was that a 1 watt or 2 watt?
I think it's 2 watt, this graph, but I'm not sure. You can reach out if you want to know the details to Michael Born from the AI.
I'll ask him on Tuesday.
Okay, so we are only 1 minute over time. Let's move on. So next up, we have Quentin Barry, who was in NASA Goddard, and he abandoned that to come back to France. So he's in the Française Atomic Energy Commission. He's very involved in LISA data challenges. But today he will tell us about blind cancellation of laser noise. So go ahead, Quentin.
Thank you. Can you see my slides?
Yeah, I can see your slide, but not your video.
Oh yeah, sorry. Yeah, I forgot to do that. Okay, here's my video.
Thank you.
Okay. Well, thank you. Thank you for giving me this opportunity to talk today. Hello, everyone. So yes, this is about blind cancellation of laser noise for space-based gravitational wave detection in general, and for LISA in particular. And this is a work that has been carried out with, yes, my Goddard colleagues that I abandoned, John Baker, Jacob Slutsky, Ira Thorpe. Here today, I will give you a very quick overview of the state of the art of the time delay interferometry. Of course, I won't describe again what is TDI, because we had very good talks from Martina and Olaf before, so you know everything. I will focus on the idea that is behind this blind time delay interferometry technique that we've come up with, and I'll present some performance assessments and some perspectives for the future. So the idea, well, the objective is still the same, right? It's to fish for these very small gravitational waves, which are deeply buried into the laser noise. And the solution to do that was proposed by Tinto and Armstrong in 1999. And since then, there have been extensive analysis of TDI, and including, you know, how to optimize the sensitivity, how to remove laser noise when arms are flexing, etc. And more recently, there have been studies about the several effects, and we've had two presentations about like the clock synchronization from Olaf, and also the construction of null channels from Martina. And so there's been also other studies about the effect of filters, for example, from Jean-Baptiste. And this list, let's say, of studies shows us that TDI is not a trivial thing, right? And this is a crucial step for the mission that we have to study properly. And so that's good also to have some alternative thinking about it. And there have been different ways of looking at TDI already. There have been algebraic approaches, so, you know, considering TDI as a solution over the ring of polynomials by Vinet et al. In 2002. And then Romano and Wong in 2006 showed that there is a relation between principal component analysis and TDI. And then we've built on this idea recently. So they've been this new definition of TDR, numerical definition from the design matrix, which is to say the matrix that encodes how laser noise enters the measurements. And this is called TDI infinity. We separately proposed a derivation of TDI-like combinations from the laser noise covariance matrix. So it was a statistical point of view. And we did that in the frequency domain, allowing us to do data analysis and also TDI ranging. But then we kind of upgraded this idea to make it more model independent. And we come up with this data-driven principal component interferometry, as we name it, or PCI, and we demonstrated it with fixed arms. Since then, so it was in 2020, well, one year ago. Since then, we've developed this method, but to work with flexible arms. So meaning like to have the equivalent of second generation TDI. And this is what this talk is about. And here I want to stress the importance of, I think, of having this model independent technique. It's because it does not rely on any measurement model. It does not rely neither on the interspacecraft delay measurements. And therefore, it is robust to any modeling error, because if you have the tiniest error in your TDI combination, you may not achieve laser noise cancellation. And so we think that it provides a complementary check to conventional TDI, which is good to have for such a crucial step in the post-processing. Let me now present what is the idea behind this blind approach. And to do that, let's look first at what TDI does. It performs linear combinations of delayed phase matter measurements, which are tailored to cancel these laser noise terms. And here I have labeled in any TDI channel A alpha, which is produced by this linear combination, which involves, of course, coefficients, and then delay operators that depends on the delay, that themselves depend on time, and interferometric measurements, so phase measurements. And so in practice, of course, we have discrete data. So these delay operators have to be written down for discrete time series. And this is achieved with fractional delay filters, which have some finite half width NH. And basically, it's the number of measurement points that you need to perform your interpolation. And so this drives the accuracy of the interpolation. And so if you inject this, fractional delay filters into the first equation, you obtain the second equation with a fractional delay filter coefficients. And now the delay operator are just integer delays, right? You're just shifting your data by a fixed amount of samples. So if you gather all these this equation, or let's say all these integer time shifted data into a single matrix, a data matrix, you obtain this equation. So X here is the data matrix that contains the version of the data and the NH version of the data that are backward shifted, and NH versions of the data that are forward shifted. And so you can write this a very compact expression involving this data matrix X, and also correspondingly the vector of coefficients that I name here G alpha. So here you have the matrix of shifted observation and vector of coefficients. And the idea behind a data-driven principal component interferometry, or PCI, is to find some alternative to this TDI variable A, by exploring general combinations of the data matrix X. And these general combinations are informed by the data, looking at the correlations that are in the data. But how do we do that when we have time dependent coefficients? So the trick is a bit like in second generation TDI, we have to approximate them by approximate these coefficients to tailor expanding them at first order in time. And we can get the same equation as before if we do that. If we redefine the data matrix X with this new data matrix Z, which contains X and X times the vector of time. So basically you have moved all time dependence into the data matrix, and you have now a constant vector of or matrix of coefficients G. So the aim then is to find a G from the data. And so to do that, we perform the principal component analysis of the data matrix Z, which is basically doing the singular value decomposition, Z equals U times S times V transpose, and S here is a diagonal rectangular matrix. And actually doing this operation is known in the data processing literature as singular spectral analysis, or SSA. And if you look at what are the singular value, you see that they can be ordered in decreasing amount of variance. So meaning that you are recombining your data, ordering them in according to the amount of noise that they carry. And we've done that for principal component analysis of 0th order in time. This was our previous work in blue. And now we've done that also for first order in time, which is shown in orange. And the idea is still the same, is to concentrate really on the lowest variance components and discarding all the other ones. And once you've done that, you can take your single link measurements, which are here in blue, dominated by laser noise. And so to generate them, we use the LISA instrument generator by Jean-Baptiste and Olaf and Martin. And this helps us to, allows us to construct this data matrix Z. And then we compute the singular value decomposition of Z and project the blue data onto the lowest variance components. And we obtain these orange and green results here, which are the principal projected principal components. In orange, you have the 0th order, and in the green, you have first order. So you see that you're suppressing some dominating noise here. But if we want to assess the performance of our algorithm, we need to compute the gravitational wave sensitivity. And that's, that's doable because any waveform that you have in the link measurements can be simply transformed using this linear, transformation. So you apply that to the Z matrix, the data matrix that contains the gravitational wave data, and you multiply it by V, and you obtain these principal component variables. And here we have, to check that, we have generated, actually, as Martina, stochastic point source in the sky with LISA GW response. And we obtained the blue curve once we transform it in PCI, sorry. And we have also overplotted this analytical model that we can derive from the same transformation, knowing the PSD of the injected signal. And so this allows us to then compare the gravitational wave sensitivity of first order PCI with the second generation TDI combinations. And so to do a fair comparison between the two, we need to adopt a definition of the sensitivity, which is maybe slightly uncommon, which is defined as the variance of the gravitational wave strain amplitude as it would be estimated by a generalized least square estimate. This just allows us to do a proper orthogonalization of both TDI and PCI, because maybe, as Mauro will tell us, the AET are not always orthogonal. So we want to make sure that we are dealing with orthogonal variables here. And so basically, with this definition of sensitivity, you have an expression like this. SH is given by this expression, but I won't go into the detail of that. So what we obtain when we do this computation, both for TDI and for PCI, is this curve, sensitivity as a function of frequency. And yes, for me, this is kind of mind-blowing, because to compute the orange curve, we haven't used any information about how laser noise enters the data, and what are the delays. And however, we obtain theoretically a very similar sensitivity as second generation TDI. So that's encouraging. And we decided also to check that with the simulation, so like empirical values. And so we actually, with this definition of the estimates of the strain amplitude at each frequency, we can produce time series of estimated strains as a function of time or as a function of frequency. We can convert that in the frequency domain. And this is what is plotted here. You have, so the blue curve is the same as before. This is this analytical sensitivity model. And in black here, you have the PCI data, which is computed with this least square estimate, and just projecting the single link measurements onto the principal components. And in gray, we have computed the TDI version of that with Pi TDI, which is this software developed by Martin Stab to produce second generation TDI combinations. And you see that they are very similar and follow quite closely the analytical model. So this is encouraging. And as a conclusion, I will tell that we developed a data-driven algorithm to cancel this laser noise with varying arm length. And we are simply performing principal component analysis on a data matrix that contains versions of the data that are shifted by integer numbers. And this is, we achieved that for varying arm lengths by including first order in time. And we obtained the same theoretical sensitivity as TDI, checked with a handful of simulations, but of course we have to check it more extensively by doing more simulations, and also by constructing a laser noise residual model analytically. And we want to better probe the impact of the data size and stencil size, so this number of shifts that we use in the analysis onto the performance. We want to probe these hyperparameters, and but this is still an entirely model independent method. And so in the future, we want also to demonstrate that gravitational wave parameter estimation is possible with PCI. And this is, I think, something which is required to fully convince people to use it. So thank you very much for your attention. And if you have questions, I'll be happy to answer.
So thank you, Quentin. And yeah, you cleverly sneaked in a crash course on matrix operations in your talk. That was very clever. So I don't see any hands raised. I saw some compliments for you. There was one remark I see from Jean-Baptiste. Maybe you should call first order PCI PCI2 because it's equivalent of TDI2. I have to agree to that.
What about calling TDI2 TDI1? No, I'm joking, but for me it made more sense to call it like that. But I agree, it would be less confusing.
Okay. All right. So we have two hands raised, but let me continue the tradition of just asking my own question first. So, what is, in your opinion, the best TDI algorithm if you want this operational onboard? You are muted, Quentin.
Oh, I'm sorry. Sorry, wrong button. I mean, I think if you have a faithful modeling of your instruments and good accuracy in your estimates of the time or of the delays, I think that's good to use classic TDI second generation, because you have a classic geometric interpretation, and it's physically more understood. However, I think that if with in-flight data, for some reason, the first attempt in applying TDI doesn't work, then we have this second recipe to use to see if we can recover, if we can cancel laser noise, right? And that will give us hints or leads whether this is some instrumental problem, or this is just some processing problem. So I think in that sense that the both are complementary, right? There is not something that is better than the other, I guess.
Okay, well, that was a bit dissatisfactory answer, but let's take the hand-raised question. So
Sorry.
Olaf, please go ahead.
Yes, thanks for this. Very nice, very interesting results. I've seen them before, but still very interesting, at least part of them. I was wondering, what is the performance in terms of processing time for this version, for this processing compared to standard TDI?
Yes, so this is a few minutes. So actually, the performance it's more stringent. I mean, it's more demanding in memory than in CPU time. Would be like to produce these plots, you have to wait like 1 or 2 minutes, or 1 minute. I don't remember, because I use a lot of memory. But actually, sorry, because I have separated like the computation in several sub-computations. You can do principal component analysis in by stretch or by segments, and this allows you to not to eat too much memory. But I guess there are ways of speeding up the computation, especially with more adapted algebraic routines, or with GPUs. I think we could do that very quickly. It's a bit like in TDI, actually. If you're working out a matrix-based version of TDI, then you can make use of some fast algebraic transformations, right? Codes.
Yeah, okay, it's much faster than I thought. Thanks.
Okay, so we're already 2 minutes over time, but well, we don't need the entire 15 minutes for coffee break, right? It's overrated these days. So let's take Jean-Baptiste's question.
Well, sorry.
With an echo.
Okay, sorry about that. 2 mics, 2 speakers.
That's better.
Yeah, so you probably answered half of my questions, but just looking forward and looking to the analysis of gravitational wave in this PCI framework. Now you probably want to cut your data to only conserve the low variance eigenvectors, right?
Yes. Yes.
Is there a way, because these eigenvectors are fixed once you've run your PCA, is there a way to marginalize over their uncertainty, because you cut them to a certain point, so you made the decision basically on the way you write your likelihoods, and another way to say it, you have a point estimate on your arm length. Can you include in your analysis the fact that there's some uncertainty in that?
So this is a good question. Actually, John Baker was thinking about that, like how to fold this into a Bayesian framework. So first of all, like to select your, how many principal components you need, you can compute your SNR or your sensitivity, and you see that after some number, like this is usually 6 for full sensitivity, or 3 for a good enough sensitivity, or like 90% of the sensitivity. Then you see that adding more components doesn't improve your sensitivity. So this is the first thing. And how to I guess I mean, the way we are this is a linear transformation, so we should be able to assess the uncertainty of the principal or the let's say the elements of the eigenvectors, and then transform that into a Bayesian scheme where we are expressing the posterior distributions of these eigenvectors, and so you would get at the end some distributions of residuals of laser noise free residuals, let's say. Something that you could do with TDI ranging. I guess that was your idea.
Yeah, maybe.
Okay, well, maybe we can talk about that
Thanks, Quentin.
offline.
So wonderful. We ended up with a very engaging talk and conversation. So I thank all the 3 speakers, Martina, Olaf, and Quentin. And so we're 6 minutes over time, but that's fine because we only have 3 more talks to go. I say let's go for still our 15 minutes of deserved coffee break, and we meet here at 4:20. Is that okay, Elsder?
Perfect.
All right.
Perfect.
Thank you.
You
Sorry
also-
for being late.
Well,
Don't worry about it.
so just a reminder, please unmute yourself and unvideo yourself for the coffee break.
Oh, actually, you don't need to. No one will be seen other than me as I'm talking at the moment.
Hello?
Okay, I'll just stop sharing so that you can practice.
Sure. Can you see my screen?
We can see the application as well as the slides.
Now, just the slides, I suppose.
Just the slides, yes.
Great. So it's
And it's advancing through.
okay. You see my cursor, right?
Yes.
All good then.
Oh, we see all the typos.
Which typos?
No, no typos.
Do you want me to keep sharing or should I stop?
I think stop, and then I'll put the coffee thing back up just so that people know that it's still the break.
Okay.
Sorry, I almost called you Marco, but Mauro.
Yeah, Mauro. It's one of the most difficult names to pronounce for non-Italian speakers, I guess. This is AU, which is pretty tricky, it seems.
I was thinking like the New Zealand Maori. Oh. Although I could also claim that it's my Italian heritage, but
probably that helps. I mean, when I was in France, that was really, a problem for people to pronounce. It was most of the time called like Moreau or something like that.
Yeah, well, I can tell you people have struggled with my name over the years. But the best story of names not traveling or being converted well was Ewan Fitzsimmons and I were in the Lisa Symposium. It was in California. I can't remember which year it was. And we went into a Starbucks and, they ask for your name. So I said Ali, that was fine, got that. And then they asked Ewan and he was like, Ewan. And the person was like, sorry, Ewan. And eventually they gave him a cup with U.N. on it. I'd never heard the name Ewan before. I'm beginning to think that we should have called 2 sessions TDI, just 1 session Lisa data analysis.
Yeah, kind of quite TDI oriented.
Yeah, these the last 2, quite. I mean, it's a very important topic, and we need to get it right. So, I do think Lisa data analysis gives a slightly misleading sentiment.
Well, I'm also showing a couple of parameter reconstruction plots, so I'm really doing a little bit of data analysis too, but
I'll let you off then.
that's not going to be the main point to talk. So I'd say the name of the session. So you said Italian heritage, which area of Italy? And
my grandfathers, but my mother's father's family were originally from Pisa.
Okay.
Actually, something like 95% of all the Italians that live in Glasgow are all from the same area in and around Naples, somewhere in the Tuscany, sorry. I don't know what happened, but basically the story goes that a small number of them came to Glasgow and then they sent word back home that it was good. So more of them came, and the end result is that like almost all of them have heritage from there.
I mean, Italians tend to cluster, that's true. But in general, I suppose when, you're immigrants, you tend to go where you know other people, no?
Yeah.
In general.
So we have 1 minute, and I noticed that the number of attendees have dwindled a little bit. Hopefully they come back on, or they didn't go to the wrong link.
I
need to say that the redundant or the second link post coffee break
is the same.
No, it's different in the Google Sheets, in the program. The password is different. So I sent around an email to just keep to this link.
In the Google Sheet.
Okay, so it's 4:20. Let's begin. Do we have the recording and live everything on, Alistair?
Yes. The coffee area will be the coffee break section will be chopped.
All right. Wonderful. Okay, so we start the second and the last LISA data analysis session with Mauro Pieroni, and he is in Imperial College London. He will tell us about the orthogonality and non-orthogonality of TDI channels. Yeah, so please screen share and tell us about it.
So, do you see my screen?
Yes, good. And we hear you, so all good.
Okay, so, well, first of all, thanks. I would like to thank the organizers for the opportunity to present my work here today. As you already mentioned, and as you can see from the title, I'm going to talk about the non-orthogonality of LISA TDI variables. This is some work I'm doing in collaboration with these people, and hopefully it's going to be out on the archive in the next couple of weeks. So this is an outline of my talk. I will start by saying a few things about detection and characterization of stochastic backgrounds at LISA in general, in the simplest scenario, meaning equal arms and equal noise levels. So I will tell you a few things about the noise model and the response function and how to compute the strain sensitivity. Then I will move on to more realistic things. So I will allow first for unequal arms and then for unequal noise levels. And I will then move on to conclusions and future perspectives. Given the audience, I won't spend much time on this. I suppose you all know a lot of things on LISA, probably more than me. The only thing I wanted to say, since I'm a cosmologist, is that for cosmologists, LISA is quite a wonderful instrument. You can do a lot of cosmology with it. And in particular, and this is what brought me to this community, you can, if you manage to detect and characterize stochastic backgrounds, you can learn a lot of physics out of that. So let's go a little bit more into data-related things. In the following, when I will say things about data, I'm always assuming my data to be in a frequency domain, and I will always assume my data to be a superposition of signal and noise here. Assuming signal and noise to be Gaussian, all the information I want is in the 2-point function, which assuming signal and noise to be uncorrelated, I can expand as just 2-point correlation of signal and 2-point correlation of noise. The latter is what we typically call the noise power spectrum. For the signal side, things are a little bit more complicated because you have the signal power spectrum, which is modulated by the instrument response. I will tell you a few more things about the response in the next few slides. But what you can do in general is to collect the response so that you define this new quantity, the strain, which is something you can directly compare with the signal. So this quantity is what LIGO people, for example, normally show in their plots. One more remark, cosmologists normally like to work in omega units, meaning they convert energies to the they normalize energies to the total energy density in the universe, so critical energy density. That's how I'm defining this omega quantity. And same thing you can do for the noise. So you can just define the sensitivity in the same units as the signal. Okay, so moving on to even more data-related things. What you need to do to achieve the required noise level is to perform some operation to get noise reduction. And this is what is TDI, time delay interferometry. two of the possible choice you can do are the ones I'm showing here. So Michelson TDI variables or Sagnac variables. Michelson variables are typically dubbed XYZ, Sagnac alpha, beta, gamma. So Michelson is something very simple. It's just comparing what's happening along one arm compared to another one. So basically this thing versus this thing. Then you can add some extra loops to compensate for Hall effects. On the other hand, Sagnac variables are just one loop in one direction versus the same loop in the opposite direction. So very plain and simple. Actually, if you try to use these variables, what you learn is that they are correlated. So you would want to move onto a basis where your variables are orthogonal. And these are the so-called AT variables, which on the other hand, I'm dubbing with this math called AT for the Sagnac variables. And in the equal arm case, you can do this by using these very simple transformation metrics. One last variable I would want to introduce is this zeta fully symmetric variable, which is a signal orthogonal variable, like the T variable for both Michelson and Sagnac variables. I will tell you a bit more about this in a moment. So let me first tell you a few things about noise. The noise that we consider later on is basically coming out of two components. There's going to be an acceleration noise and an interferometric noise. Basically, as I will show in a moment, acceleration is going to dominate at low frequencies in most of the variables, and interferometric is going to dominate at large frequencies. Acceleration is basically related to the deviation from free falling for the test masses, and interferometric is just laser noise. What I can do is to compute how these two noise components propagate into the TDI variables. So, for example, I can compute how they contribute to the XX correlator. And what you learn is that basically you just have OMS with some prefactor, same prefactor for acceleration, and another term here, which at low frequency is just a constant. On the other hand, if I compute the same analogously, if I compute how these two components propagate into the TDI variable, I see that there are some different contributions here. And as I will show in a moment, these are gonna modify the ratios between the acceleration and noise levels in this TDI variable. So if I just plot the two noise components in the left, you see that basically acceleration is larger than OMS at low frequency and vice versa at large frequency. So since in XX, for example, they just appear as these plus 4 times acceleration, as expected, acceleration dominates at low frequency and interferometric dominates at large frequency. If I expand this term here for TT, on the other hand, I get basically this factor, which is F frequency over F star. F star is the characteristic frequency of the instrument, which is 0.2 milliar, so 0.02 hertz. If I plug this factor here, basically I can see that the acceleration noise component is suppressed compared to interferometric in TT. This was also shown by Martina in her talk before. Okay, so going on to the response, the assumptions I'm using here in computing the response are isotropic spectrum and non-chiral. Isotropic means the same from all directions, and non-chiral means left-right components are the same. The response is basically has the structure. So there's going to be a factor, which is depending on which quantity I want to use as the measurement. In particular, I'm using fractional frequency. Then there is a factor here, this R tilde, which is just carrying geometrical information depending on which kind of TDIs I want to use. And there is also this other factor, the W, which on the other hand keeps track of loops in the definition of my TDI variables. In this left plot here, I'm showing you the geometrical factors for different TDI variables. As you can see, for most of them, it's basically, it has a very simple structure. It's just flat, low frequency, and then it goes down at larger frequency. So basically, you can think of this as some kind of low-pass filter. The only variable which is behaving differently here is T. And you can see that low frequencies, here T goes to 0. So this is why T is said to be signal orthogonal. Basically, I have no response to the signal at low frequency. In this other plot on the right, on the other hand, I'm showing you the full response. So when I plug back all these other factors. Now that I have the response, I'm able to compute the sensitivity just by dividing the PSD by the response. This is what I'm showing in the left plot here. In particular, what I'm showing is in green is the full numerical response. In black, I'm showing an analytical approximation obtained by expressing the geometrical part as this very simple function. And in orange, I'm showing you how much the noise level changes if I allow for 20% variation in the two noise parameters. As you can see, analytical and numerical match quite well. Actually, they match within this 20% range for the noise parameters. In the right plot, on the other hand, I'm showing you again the noise, but this is going to be in omega units. So this is the sensitivity that cosmologists typically use. Okay, that's pretty much it for the equal arm case. Let's move on to more interesting things. In reality, we won't have equal arms because orbits are, I mean, along the orbit, there are going to be fluctuations in arm lengths, and this is going to lead to breaking on the orthogonality between the different TDI variables, as I will show in a second. In principle, you can compute analytical approximations for these to test the numerical results, which I will show in a moment. Okay, let me start by explaining you what happens for the different TDI variables. So in all these plots, I'm showing solid lines which correspond to equal arms, dashed lines to unequal arms. First row here is going to be X, Y, Z. So you can see that going from equal arms to unequal arms is not changing much the signal response, the noise spectra, and the strain. On the other hand, when I move on to the AIT basis, so onto the orthogonal basis, you can see that T is actually modified quite a lot. In particular, this is visible from this plot here, where you can see that while T was supposed to be matching with Z, so supposed to be signal orthogonal, at some point, this orthogonality is broken, and basically it goes back, it matches with the other two variables. Z, on the other hand, here can be seen to be way more robust to corrections due to unequal arms. Similar thing happens for alpha, beta, gamma. Again, first line is alpha, beta, gamma variables. Sorry. Second line is the orthogonal combinations you can obtain out of alpha, beta, gamma. Again, you can see that some deviations from the equal arm case happens in the noise orthogonal variable, but in this case, this variable seems to be way more robust than the Michelson ones. So good news. Other things that are interesting to notice is what happens when I want to study correlations. So in this plot, I'm showing you what are the noise correlations. In particular, I'm showing you the off-diagonal elements divided by the on-diagonal elements, square root on the on-diagonal elements. Again, solid lines are equal arms, dashed lines are unequal arms. In both these plots, and same for the next line, they are supposed to be 0 because in the equal arm case, AT is orthogonal, and same goes for AZ. And analogously, alpha, beta, gamma, and their orthogonal variables. But you can see now that when I look at the unequal arm case, off-diagonal terms become sizable, and in particular for terms involving T in the Michelson variables, they become close to order 1. So this can be problematic. Same thing is not happening if I replace T with this Z variable, and same goes if I use this orthogonal variable built out of the Sagnac variables. So both Z and these AT variables built out of Sagnac seem to be way more robust than standard Michelson variables. In this plot, I'm showing you what happens for signal correlations. In this case, it seems like all the variables lose orthogonality when I go on to unequal arms. But keep in mind that for Z and for T Sagnac, T is still signal orthogonal. So the fact that signal correlations become large is not really such a big deal as in the Michelson case. So even if signal correlations are large, it's not very problematic until signal is suppressed in all the combinations involving T Sagnac or Z. Okay, so one extra thing I want to show you in the unequal arms, equal noise is what happens if I try to attempt some signal reconstruction. So here, what I'm doing is to inject some signal, just a flat signal with some fixed amplitude. This is a quite large signal. The SNR is ordered a couple of hundreds. For the reconstruction, what we use is just the diagonal elements. So we want to see what is the impact of neglecting correlations in AEZ, AET. AEZ, we know that is more or less orthogonal. So the error we're doing comparing to the full correlation matrix is not going to be huge. On the other hand, in T, we know that there could be some impact. You can see from the left plot that the reconstruction of both noise and signal is decent. From the right plot here, which is my corner plot, you can see that basically with T, I'm underestimating a little bit the error on the acceleration component. And this is slightly leading to a slight underestimation on the error on the acceleration, on the signal parameters too. But this is not dramatic. So there is an effect, but it's not something terrible at this level. What I want to do now is to switch from equal noises to unequal noises. So I want to make my problem way more complicated. I mean, this is what we will have in reality, because I mean, each test mass and each laser will have its own noise level. So this is what we will have to deal with in reality. So let's try to see how much this will impact all the discussion I did this far. So signal response is not going to be impacted by this, but noise correlations is going to be impacted. So let's first look at this. Keep in mind that for the equal arm case, both in this column and in this column, we are not expecting to see nothing for cross correlation for in the equal arm case. On the other hand, adding unequal noise levels is making the equal arm noises correlated. This is already one big difference. Second thing, when I allow for unequal arms too, the interesting thing is that basically the for all the variables which we know are going to be reasonably robust, the estimations we did in the equal arm case are basically matching to a good degree to the quantities we computed for the unequal arm case. So this is quite nice news. Finally, one last plot I want to show is, again, a reconstruction using all the parameters simultaneously. You can see that I'm still reconstructing the signal reasonably well. You cannot really see the error bands, but they got a bit larger, but not crazy larger than before. So good news. If I look at the reconstruction on the noises, what they see is that, so for acceleration noises, it seems like in some cases, AT is doing better than AEZ and vice versa. If I actually look at the eigenvalues of the Fisher matrix estimated from the MCMC samples, I see that in reality, AT seems to be seems to be giving an information which is a bit larger, again, because I'm ignoring correlations. But again, this is not too terrible. On the other hand, in the P parameters, in the interferometric parameters, systematically, I always see that the noise is underestimated in AT compared to AZ. That's pretty much everything I wanted to say. So let me draw some conclusions. Equal arms, unequal arms compared to equal arms can change some things, break orthogonality. We must be careful with this. Reconstruction of signal parameters and noise parameters can be affected, but it seems like it's not too terrible at this level. Concerning future perspectives, here I did a bunch of assumptions. In principle, we would want to drop as many of those as possible in the future, take more realistic noise models, allow for time dependencies all around which I've neglected. So there's a lot of work we should be doing. And that's pretty much it. Thank you very much for your attention.
Okay, wonderful. So we have 2 minutes for questions. So either write up or raise your hand. And we have Jean-Baptiste again. Go for it, Jean-Baptiste.
All right, me again, but this time without feedbacks. Thanks, Mauro, for this talk. Just a silly question. Doesn't what Quentin presented, PCI and or TDI infinity, just solve exactly the problem that you have here? Because they will account basically in the way they diagonalize their covariance matrix for these potential correlations or unequal arm length and so on.
Well, I mean, in principle, the thing is, if you use the full correlation matrix, things are going to be equivalent in whichever basis you use. So if you manage to produce something which is fast and stable, we are happy. The main thing is that if you want to do diagonalization numerically on the fly, that can be kind of unstable, because I mean, if you look at the responses, for example, you know, this guy can become much smaller than this, and depending on the frequency, you can even hit numerical precision. So, I mean, of course, if you do things properly, everything is going to be equivalent. The point is, if you manage to make sure that everything is fine, good.
Yeah. But the thing with PCI and TDI infinity is to cut basically the parts of the space which have a very big variance, basically, so that you try not to hit those numerical stability problems, right?
But it's not a problem of variance. Here is really, even the analytical computation is going to be tricky, because I mean, when you switch from, say, let's stick with Michelson. If I want to switch from XYZ to AT, I mean, if I go to low frequencies, the difference between AE and T can be so large.
Excuse me, but I am going to need to interrupt this. We're already 1 minute past, and this sounds like a very lively discussion that merits its own discussion. So maybe Jean-Baptiste, and you can take this offline. I want to sneak in Quentin's question. So go ahead, Dr. Baghi.
Yeah, hi. Yeah, thank you, Mauro, for it. It was very interesting. Actually, yeah, very to quickly follow up on that. In PCI and both in TDI Infinity, we're computing the principal components of the either the covariance of the laser noise covariance matrix, or the laser noise covariance matrix, or the laser noise design matrix. So all the secondary noises are not taken into account in the first step. So I think we have basically the same problem. In the end, we need to have a robust estimate of the secondary noise, the non-laser noises, to do this proper orthogonalization. And I was wondering, for the unequal noise level case that you investigated, like how much different were the noise levels, and could you state again what was the impact on the noise correlation? I didn't get that, I think.
So for the parameters, I generated Gaussianly all the parameters with the same mean and a variance, which and a sigma, which was 20%. So in the end, some parameters were even like twice others. So let's say mean value was like 3 and 15. Some were from 2 to 6, and some were from 10 to 20, for example. Can you say again the part of noise correlations? I'm not sure.
I mean, and so these, with this level of discrepancy, then what's your change in noise correlations? I was not sure what was the dashed line and solid lines.
Okay, sorry. Solid line are again equal arms. Dashed lines are unequal arms. Basically, I mean, what is changing is that in the equal arms, equal noise levels, solid lines are all 0 in these two columns. Here, because I'm introducing these different noise levels, I cannot really orthogonalize perfectly the noise matrix. I mean, I can still do it, but it's going to be different. I cannot just use the standard rotation matrix. That's the point. The interesting thing is that the unequal arms for these three variables seems to be more or less the same. So it seems like these variables are quite robust, even if you allow for different noise levels. The estimate you would get seems to be pretty good.
Okay, yes. So in these plots, you're not comparing unequal levels and equal levels of noise, but equal arms and unequal arms. Okay.
Correct. For unequal noises.
Yes. Okay.
All right. I think that's a good point to stop and move on.
Thank you very much for the questions and for the chance to speak again.
Good. So next up, we have Martin Stab. Martin Stab, he is a mature PhD student in AEI who should be writing up his thesis. He has been very productive, but he's a prized PhD student in AEI, and he will tell us about time delay interferometry ranging. So the boring two-dimensional screen is yours, Martin. Go for it.
Yeah, thanks, Shweta, for the nice introduction. So yeah, I will be talking about TDIR that was already mentioned by Quentin earlier, and yeah, especially about the tone-assisted variant of that we came up together with Jean-Baptiste, Sam, and Bob. So I also have an introduction slide for TDI, but I will make it quickly. So basically, yeah, LISA is designed such that we only measure one-way measurements. So the two most important measurements in this presentation are the interspacecraft interferometer, which yeah, relates the far laser to the local laser, and the reference interferometer, which relates the adjacent to the local laser. And by connecting them, by gluing them up together again in post using TDI, we can synthesize those yeah, equal arm interferometers. And on the bottom right, you can see the first generation Michelson combination that we can achieve by doing that. And to do that, we need the ranges, which are yeah, basically the same, yeah, which are used to propagate measurements from one spacecraft to another, and those are then these delay operators. And TDI ranging is basically somehow like inverts this concept. So you're trying to find ranges that remove the laser frequency noise from your data, and you don't know them a priori. So you're trying to find them by just yeah, changing them and trying to minimize the residual power in your TDI combination. And the accuracy of that technique is ultimately limited by secondary noises in your interferometer. And this is just an overview of some more standard TDI estimators where a lot of literature already exists now, or like 5-4 papers, I'd say. So the first one is the one Tint et al. Developed. So you just take your first generation Michelson or your Michelson X and calculate the power and try to minimize this expression with respect to your delays. So this assumes constant arms. So it's basically 6 parameters that you're trying to fit. And then you can take it further and just take X, Y, and Z, so the full TDI space, and do the same thing. And you will end up with more accurate estimates of your arms. And then the third option is then what already Quentin talked about. So this PCI, where you yeah, orthogonalize those 3 combinations and also widen them. So you also take into account the yeah, the noise spectra of your secondary noises. So here we're looking at the tone-assisted variant. So an idea was to inject a tone into your primary laser. So we're now in a locked configuration. So we only have one laser frequency noise that we have to cancel, which comes from the primary laser. And we inject a tone to arbitrarily increase the power of laser noise, or yeah, the power of laser noise in your yeah, measurements, because higher laser frequency noise means you can estimate your TDI combinations or your arms better. And so you not only have the laser frequency noise, but also a sum of several tones. And we set the tone amplitude of those tones to 10 kilohertz. For comparison, the laser frequency noise is roughly a root mean square of 100 or so, 100 hertz. So it's slightly above the laser frequency noise level. And we can also see that in some simulations I was running. So in blue, you have the raw measurement, one ISI, one is a spacecraft interferometer. I think it's the one on MOSA 1.2. So you can see the wide laser frequency noise at 30 hertz per root hertz modulated with the round trip transfer function since we're in a locked configuration. And on top of that, those two tones at roughly 0.7 Hertz. And if you form your TDI variables now and you have an error of, let's say, 10 kilometers, then you end up with this dark red curve, and you can just see how laser frequency noise got suppressed, but not fully, since the dashed gray line shows you the level of secondary noises. So this would not be enough. Knowing the arms with 10 kilometers accuracy would not be enough. And if you just plug in 10 meters, you can see that the laser frequency noise is below the secondary noises, but those tones still stick out. And we can use this property to be still sensitive to any errors in the arms. And before we would not be anymore, since laser frequency noise is basically now buried in the secondary noise. And we also formulate estimators for those cases. So first, this equation shows you the technique we use to read out the tone amplitude at a specific frequency. So it's basically just a finite Fourier transform, which is also windowed. And we do that for both tones and for all three TDI combinations. And then we just sum up the modulus squares of those amplitudes to basically also just have a value for the total tone power in all three TDI combinations. And we try to minimize this to find the 6 arm lengths. And we can do something similar to PCI, but in this case, it's much simpler since you only have 6. So we have 3 tones, 2 tones and 3 combinations. So it's 6 values that we have to orthogonalize. So this is much easier to do. We just weigh it by the TDI, by the PSD of the secondary noises. So high secondary noise means that we weigh it less into the total power in the end. So we found out that a minimum of 2 tones is required to estimate all 6 arms. Otherwise, you get degenerate directions. And you can only estimate 5 arms or 5 combinations of the 6 arms. And by introducing the tone, we get an improved TDIR performance because of this higher signal to noise ratio, where the signal is really the laser noise, and the noise is the secondary noise floor. Then to compare those 2 methods, so I'm comparing the standard summing up X, Y, and Z, powers in X, Y, and Z, and the tone assisted case here, the first one. So summing up the tone powers. I will compare in the next slide. So we just formulate our metric, so we know how good we are. So delta IJ is basically the estimation error, which is given by the estimated arm length minus the true arm length, and we just collect this in a vector to analyze the statistics of this. And we find that in the standard case, we have an unbiased estimator and a covariance, which is given by this expression. And we see for higher, so T is the observation time. So the higher we choose our observation time, the better our estimates are. And as N is the level of secondary noises, and as nu is the level of laser frequency noise. So basically, we are driven by this fraction. And then we have also this matrix lambda here, which just determines all the correlations between the 6 arms, and is also dependent on the locking scheme. For tone-assisted TDIR, we are still unbiased, and the covariance matrix is looking really similar, except that instead of the laser frequency noise level, we now have the tone power, which is given by this expression. So we basically have another knob we can turn to increase the the accuracy of our estimator. And that I want to show you in that plot. The left plot, it basically shows results from a simulation where we turn on laser frequency noise and or mass noise, and we use 500 seconds of duration to just make some quick estimates. So we can also choose that longer, and we repeat that 200 times to get some statistics, so to create some ensemble that we can analyze. And below you can see all the scatter plots, so the pairwise scatter plots of the errors in the arms, and also overplotted the ellipse that is a result of the analytical calculation. So this shows that we think we understand how all the parameters influence the estimation process, and we can see if we take the mean of all those standard deviations that we end up roughly at 5 to 6 meters standard deviation of in our estimates. If we now inject a tone with an amplitude of 10 kilohertz at those two frequencies, then what we basically find is that the correlations roughly stay the same, but our uncertainties drops quite significantly. So we now retrieve a standard deviation of only 1 or 2 centimeters, which just shows how much better we can get if we introduce more laser frequency noise by introducing this tone. And now I want to talk about applications of this. So there are other ranging methods in LISA. So basically there's the clock sidebands and also the PRN ranging. And important is that all ranging measurements are never measuring just the true range, but they are disturbed by several things. For example, you can have noise, or which is a random process, or a bias, which is a constant, and many are also subject to some ambiguity. So you can not determine it directly, but you have to find some integer and multiply that by the ambiguity, which is related to the wavelength of your measurement, basically, of the signal that you're measuring. And you have to determine this this integer to get an absolute range measurement. And as the best candidate in these, we have the clock sidebands, which measure the AMPRs with high precision. So they are only limited by the modulation noise, which is quite low. And the ambiguity of this measurement is 12.5 centimeters, which is just the wavelength of the 2.5 gigahertz clock signals. And so to use this measurement as an absolute ranging measurement, the only thing to do is we have to find this integer mij, which just adds multiples of those 12.5 centimeters to the measurement. And I was hoping that Olaf would talk about it in more detail, but this is also something we did in the paper he showed in his slides on TDI without clock synchronization. And there we show that you can use the PRN measurement to resolve this ambiguity or to find any offset that is unknown. And the properties of this PRN measurement show you that you have to measure roughly a couple of seconds, so 16 seconds is a rough number, to find this offset or this ambiguity. The standard TDIR, this is only, so it's much less accurate, and you can only resolve it after 6 days. So this is quite a constraint. But if you then use tone-assisted TDIR, you're back at orders of magnitude what also the PRN measurement can give you. So here we can show that TDIR can be used as a more or less equivalent fallback or complement to PRN ranging. Okay, so to summarize, this is just what I've just talked about, comparing the different accuracies of those three methods. And the big take-home message is, I think, that this TDIR can indeed be used as a fallback or complement to PIN ranging. And in the future, we want to study different topologies of the tone-assisted variant, since we think it's quite promising. So we looked at injecting those two tones in the primary lasers, which worked quite well. And in the next step, we want to also see what happens if you inject tones in the transponder logs of the other spacecrafts. Another thing is studying the impact of clock drifts and noise, since they could have non-trivial couplings if we look at the transponder lasers, and also estimate, using this method to estimate other common mode delays occurring in cables or photodetectors, which is Sam talking about in the next talk. So stay tuned for that one, and thanks for your attention.
Thank you, Martin. Yeah, so we have a full-blown 5 minutes for questions. So please raise your hand and feel free to speak, which I'll moderate. Well, since Martin Stab had his master's under my tutelage, I think I have deserved the first question. What determined the choice of your 10 kilohertz tone amplitude?
That's a good question. So we had a lot of debate about that. Oops, I hope you can see that. So I think the upper limit of the tone amplitude or tone power should really be that you're above the laser frequency noise. Otherwise, you're not introducing any more noise power or signal power into your lasers. So the lower limit would then be a couple of, good question actually, how this scales to the power spectral density, but at least you should be above, I don't know, 10 Hertz, I guess. And then the upper limit, so of course you want to make this tone as big as possible to have to get the most out of it, but there is an upper limit, and this is due to the nature of how you inject the tone. So you would have actually a backup slide for that. So you would actually inject the tone in this primary laser, which is locked to a cavity via a PDH control loop. I'm not an expert on this.
What is PDA? Oh, foundry, okay.
Yeah, it's a foundry hole. I think it's the most common method of locking a laser to a stable cavity. And the tone amplitude should be much smaller than the modulation frequency of your phase modulation you apply prior to injecting the laser into the cavity. And if you look at some rough numbers, I'm hoping I'm getting those correct. So if anyone in the audience thinks numbers are off, please speak up. So the modulation frequency is 100 kilohertz, which then is basically the upper limit, or you should not maybe. So that's why we choose 10 kilohertz, since it's just a factor of 10 smaller than that. And we hope to stay in the linear regime of things to not mess up too much this locking scheme.
I'm just giving a moment for people to raise hands or type up their question. Otherwise, I still have another question. Okay, I'll come back to you, Quentin. In slide 7, you were showing the covariance matrices. Is this a Fisher analysis or MCMC, like a real Bayesian thing?
Yeah, I think it's more closer to MCMC, but we're not just studying one realization and jumping around in parameter space, but we really take 200 realizations of the same setup and then estimate the most probable parameters, and then look at the distribution of this repeated experiment.
So Quentin, you have a question? Go for it.
Hi, Martin. Thank you. This was interesting. I was wondering, maybe you said it, but as a summary, how are the laser noise residuals comparing to the secondary noise for each of the 3 methods you talked about, like pseudo noise pseudo noise and
Mhm.
TDI ranging and TDI ranging with assisted tones.
Yeah, so I haven't looked at it numerically. So you mean those 3 cases, I believe?
Yes, I guess.
Yeah, and I think the only thing that I can say now, since I haven't looked at it numerically further, is that the laser frequency noise coupling is basically proportional to your error in arm length to the power of 2.
Okay.
So I guess it just scales.
Yes. Okay. And yeah, okay. And comparatively to the secondary noise, you don't know what is, you know, the difference with for example, the first. Let's say to have an idea of you know how it
Yeah,
compares.
I mean,
Well, I can.
yeah.
No, maybe I can look at it somewhere, and then I can figure out with the the numbers that you have here.
Yeah, I mean,
we can have a Zoom call to discuss this further.
Yes.
sure.
It sounds like an interesting discussion for sure. Unless you have a quick one-line answer, Martin.
Yeah, I guess I would think go for comparing it to the requirement that is
Yes.
given for the accuracy on your arm length. So how offsets on your arms would couple. And I'm not sure what number that is, but if you're below this number, you will cancel laser frequency noise at least to this level.
Okay.
Say.
Yeah. Okay. Thank you.
Thanks for the question.
All right, wonderful, Martin. So thanks a lot. And we are only 10 minutes late around. So we have the last talk of the session, and that is going to be by Sam Francis. He is an optical engineer in JPL. So he left Australia to go to Pasadena, and he will tell us about well, let's see. So you will tell us about uncorrected common mode delays for TDI. So we see your screen. Everything is
okay.
And we
Okay.
Yes, your presentation's up.
Great. Okay. Well, thank you. And thank you everyone for staying for this last talk of the session. So this work on common mode delays in TDI and how they potentially limit the laser frequency noise suppression was prepared with these co-authors. So there's a mix of recent research with John Baptiste and Martin, and then some historic research at JPL from about 10 years ago by Bob Spiro, Brent Ware, and Kirk McKenzie that we're building upon. So to give you an overview, we all know what TDI is, especially after hearing several talks about it in this session. But from my point of view, at a high level, TDI, the goal is to suppress laser frequency noise. And the way this works is the same laser frequency noise from our frequency stabilized laser is being measured at different times and points around the LISA constellation. And then in TDI, we're using measurements of the spacecraft separations to correct for the different delays in these measurements of laser frequency noise, applying synthetic delays and then forming combinations where the noise cancels. And so in this talk, I will be looking at an additional source of delays that is not corrected in the existing TDI algorithms. And so these delays are optical or electronic delays that are occurring after the beam splitter. So after the point where the lasers in our long arm interferometer are interfering. And so we're calling these common mode delays because they're common to both of the interfering lasers. So in the interferometer, we're interfering a laser that's traveled from the distant spacecraft and then one that's just propagated across the local bench. And both of these lasers have some frequency noise, and when they pass through the source of these common mode delays, they experience the same delay. And so this is distinguished from the spacecraft separation delays, which are differential. Only one of those laser frequencies sees that delay. Based on our estimates, this is likely dominated, these common mode delays, by photodetector group delay. This is a dispersive delay, meaning that it's going to be frequency dependent. And so I'll talk more about that later. So essentially in this talk, I'll go through and explain more about what we mean by common mode delays. I'll estimate their impact, describe some minor modifications to TDI that could be used to correct for them, and then discuss potential ways to measure them in orbit. Okay, so let's look at a simplified LISA diagram to just further explain what the difference between these two types of delays is. So this is just a simplified LISA based on the N1, 1-2 phase locking configuration. So in this configuration, down on spacecraft 1 at the bottom right, we have the laser 1-2 frequency stabilized. And for the purposes of this diagram, I've just simplified it to only show the hardware that's relevant for the measurement of the Michelson X combination. So in this measurement, really, we have one laser, this frequency stabilized laser in spacecraft 1, and we're sending along 2 interferometer arms to the distant spacecraft. With phase locking, that laser is then, or that laser frequency noise is then getting transponded back to the spacecraft 1. And so when we talk about differential delays, these are the delays that are experienced before the lasers interfere. So in this diagram, tau2 and tau3, which are the inter-spacecraft delays that we're familiar with in TDI, we would call these differential delays. And this is because if we look at the measurement of the laser phase noise on spacecraft 1 in this S12 measurement, we see the same laser noise, phi laser. This is the laser noise of our stabilized laser. But one is the prompt signal and one has experienced a different delay. So that's why we're saying it's a differential delay. Whereas the common mode delays, they're occurring after the lasers are interfering. And so in spacecraft 1, as an example, we have this extra delay tau e, which could represent an electronic delay in this measurement chain of S13. And so in this measurement, we'd not only see the differential delay, tau3 from the inter-spacecraft travel of the beam, but both of these laser noises are now going to be delayed by an additional tau e. And so it's common to these two measurements. Okay, so like I said, these common mode delays are really any delay that's experienced after the lasers interfering. And so previously, people have talked about these types of delays, but they've focused on electronic delays. And this is fair because based on our estimation, electronic delays are going to be the dominant effect here. However, just to be technically accurate, we think calling them common mode delays makes more sense because really it is anything that's occurring after the lasers interfering. And so I've listed a few possible sources of these delays here. So optical path between the beam splitter and detector is one potential source of these delays. But I think in LISA, given the way the optical benches are built, and obviously between spacecraft, these optical benches are matched very accurately, this isn't going to be a big source of delay. Instead, we think it's probably the photo receiver group delay, as I mentioned in the intro. But really, other sources could be things like the delays through the analog electronic front end of the phase meter, or even potentially things like filtering delays inside the phase meter. Okay, so now to really look at how these common mode delays would interact with TDI, I've got another little cartoon of how TDI is working. And so just in the top right of most of these slides, I've got a reminder of the locking configuration we're talking about for these particular analyses. In this cartoon, we're starting again with this phi laser. So this is the laser frequency noise of our stabilized laser. And in the microcern, it's traveling along two arms, so arm 1 and arm 2. And depending on the arm lengths or how these spacecraft are moving relative to each other, these two arms will have different frequency responses. And so these boxes are meant to represent the frequency responses along the two arms. There's obviously shot noise added when we make the measurement, but that's not too important for this. What I wanted to show is that really in the simplest picture of forming the microcern TDI combination, what we're doing is we're seeing these differential delays applied to the measurements of the laser phase noise. And then in post-processing down the bottom, we're introducing synthetic delays that are, for example, in the measurement of arm 1, we're applying an estimate of the arm 2 frequency response. And then in the measurement of arm 2, we're applying an estimate of the arm 1 frequency response. And by applying those two estimates and forming the difference, we end up with our TDI output. And this is removing the effect of those differential delays and canceling the laser frequency noise. So when we start talking about common mode delays, we're now adding an additional set of delays along these chains. And so here I'm representing these common mode delays by these boxes: measurement chain 1 frequency response and measurement chain 2 frequency response. So as I said, these delays could really be anything following the interference of the lasers on the beam splitter, but likely dominated by electronic delays. In this particular realization of TDI, these delays are not going to be corrected. So the only way they won't have an impact on the measurement we found is that if the measurement chain 1 and measurement chain 2 have the same frequency response. So if they have the delays are matched between these two measurement chains. And for a lot of components in the phase meter, for example, and the optics, as I mentioned, these delays will be matched, but we think potentially in the photodetectors, they won't be. And so based on those diagrams we had, we estimated the frequency response of TDI to small differential and common mode delays. And so on the left, this little equation is showing the ratio of laser frequency noise to shot noise post TDI. So we think for TDI, to determine how successful it is, really, we want to look at how big the laser frequency noise is after TDI and compare that to how big the shot noise or secondary noises are after TDI. And so through this ratio, we see that for a differential delay error tau epsilon, the frequency response is flat. So it's this blue line down below. So basically that means that it's really just the error is going to be linearly dependent on the size of the error we make in our estimation of the delay. Whereas the common delays enter a different way. We end up with this sinusoidal dependence on frequency for a similarly sized delay. And I'll just point out that this is, well, this lower plot is actually a plot that Bob Spiro showed at Amaldi 8, 2009. And a lot of this analysis was initially inspired by this LISA frequency control white paper, also from 2009. So for anybody working on TDI now, I think if you haven't seen this paper, it's actually still very relevant to a lot of the discussions and has a good look at a lot of the practical sides of TDI. So I'd recommend checking it out. And there's a link to the paper on Atrium, which hopefully you can follow if these slides are made available at some point. So we wanted to understand how big this delay the effect of this common mode delay would be. And so the best way to do this would be to look at the LISA system and the LISA instruments and perform measurements of the delays through them and check how consistent they are between the different boxes that are built. We didn't have access to this, so instead what we did is look to the literature, and from a paper on photodetectors, we looked at estimating the group delay of the photodetectors based on some fits to data in this paper. So paper reference down here. And so the reason the photodetectors are potentially going to be the dominant source of these common mode delays is that these photodetectors by design are limited bandwidth. So we only want to allow 2 to 25 megahertz really for the heterodyne frequency. And so the bandwidth of the photodetectors is only going to be slightly larger than that. And when we have something that has a limited bandwidth, you often introduce some group delay through that filter or through that photodetector that has a frequency dependence. And so this is the idea of dispersion, which effectively means that as we're changing the beat note frequency that we're measuring with this detector, we're going to get a different delay through the detector. And so this plot, which, as I said, is just a fit to some data, so it'd be really interesting to see what the real data looks like. But from this plot, we can estimate that for a beat note frequency from 2 to 25 megahertz, we're getting a group delay change of roughly 3 nanoseconds. And so running with this number, thinking, okay, well, we can potentially get 1 nanosecond common mode delays through these photodetectors. We ran some simulations to look at the impact of this type of delay. And so this is using LISA simulation. The plots I'll show are from a very simplified version. So we're only using laser frequency noise. And again, we're using this locking configuration that has some nice symmetry in it that allows us to just look at this Michelson X. And also we're using equal and static arms, at least for these 2 plots. So what we see here is effectively when we introduce one of these common mode delays, which is the green curve, here I'm considering a common mode delay of 1 nanosecond that isn't corrected. And I'm looking at the residual frequency noise in the Michelson combination. And what we see is that a 1 nanosecond common mode delay is equivalent in magnitude to a 1 nanosecond error in the estimation of the differential delays or the inter-spacecraft ranging measurement. So that's comparing the red and green, a similar size magnitude. So a 1 nanosecond error in common mode delays is equally as important as a 1 nanosecond error in our PRN ranging. Although there is a slightly different frequency response, which is due to the math, I guess, I showed on a few slides. So I also mentioned that if things are matched, so if we have the same common mode delays, then everything goes away. And so this is just a very simple and boring plot to confirm that, at least in this symmetric locking configuration, if we now consider the picture down the bottom left, where both these measurements on spacecraft 1 have the same tau E common mode delay, everything cancels and we don't need to worry about these delays. So really, the next part is concerned with what happens if we can't guarantee these delays are equal on the 2 sides of the spacecraft. And I think based on the frequency planning for where we expect beat note frequencies, or how we expect beat note frequencies to evolve over the mission as the arm lengths are varying, there will be times where along one arm, it will have a different heterodyne frequency to the other arm, which, if we have this dispersive effect in the photodetector, would introduce different common mode delays in the 2 arms. However, we think that these common mode delays could be corrected with very minor changes to the TDI process. And so this diagram again is showing that really all you'd have to do to correct for these delays is add this yellow box here, this step right before applying the synthetic delays for TDI. And that's just undoing the measurement chain delays in measurement chain 1 and measurement chain 2. And so this sounds easy, but obviously the complications then would be, how do you know what delays to correct for? And so there's probably several ways this could be approached. So one way could be performing ground-based measurements or calibrations pre-launch and understanding what type of delays we expect to get through these systems and how stable they are. If it turns out we think they might not be stable over time or over different temperature ranges, then something that Martin mentioned at the end of his talk just now is that we're also considering how adding some tones into the laser frequency might be able to help us disentangle the differential and common mode delays. And so the idea that we want to investigate now is that possibly with the 2 tones that Martin used in his analysis, maybe we have enough information to measure these common mode delays as well. But maybe we need a 3rd tone to do it, to really disentangle and measure all the degrees of freedom. But this would work on a similar way to the tone-assisted TDIR that Martin explained, which is we know ultimately the goal of all of this is to suppress the laser frequency noise. And so if we have these tones on the laser frequency noise, that's giving us a really strong signal with good SNR, signal to noise ratio, to suppress and minimize. And we can adjust the time of flight delays, our estimate of the interspacecraft range, as well as our estimates of these common mode delays, and refine everything until we're at a level where the laser frequency noise cancels to what we require. And so this is just a very quick flashback again to like 2009 when Bob Spiro talked about some of this. So we found on the JPL LISA testbed, which is this testbed used for experimental demonstration of TDI, that we do see these common mode delays. It was found that to get the best laser frequency noise suppression, a 23 nanosecond delay was needed in addition to the other TDI delays they were using. And the lower right plot is just showing that as this
Sam,
delay. Yep.
Just interrupting you to give you a heads up that you're actually 2 minutes over the 20 minutes. So if you can wrap up quickly, that's and don't worry, we will leave the room open. So yeah, I see there's 2 more slides. If you wrap up, then we can.
Yeah. Okay. Luckily, the end slide is the conclusion. So yeah. So the last point here is that we saw this dispersive effect. Conclusion. I don't need to go through this. We've all heard it. So we're looking at these common mode delays, and really the future work is we're continuing these simulations and trying to understand particularly what happens when we start looking at configurations without this symmetry. We want to study, can we disentangle these delays by using these tones? And then also potentially once we start thinking about phase locking between spacecraft, are any of these electronic delays or common mode delays going to be a problem there? Okay, well, thank you very much, and sorry for running over time.
Thanks, Sam. That was a very interesting talk. I was just curious actually about the, okay, I see Olaf has raised a hand, but I was curious about, so this is purely data analysis for common mode laser noise reduction. Have you thought about how this is feasible in practice? So have you designed with FPGAs and lasers and whatever else is necessary in experiment to verify the data analysis actually you've done?
Yeah, I suppose some of the initial thoughts came out of those JPL LISA test bed experiments, it's an optical test bed with FPGAs, FPGA phase meters measuring the laser frequency noise. And it was found in those results, or in the analysis of the data taken there, that these additional electronic delays were needed to be accounted for. In terms of developing algorithms or anything to deal with it, it does just become a post-processing thing, provided we're able to measure the delays or have some idea of how big these delays are. It's just an additional post-processing step.
Thomas, do you have a comment to that?
Not really, no.
Okay, no problem. So yeah, Olaf, you have a question.
Yes, thanks for the interesting talk. I had two questions actually. One of them, you say that the photodetector dispersion you think is the dominant effect. Do you think that's something that can be well characterized on ground before the flight, such that we could, since we know the beat node frequency of each beat node, we could simply apply a known correction?
Yeah, I mean, that would be an ideal way to do it. I suppose our estimate is really just like a fit to some data in a paper. So I think the thing to do would be the people working on the photo detector would want to characterize this and understand how repeatable it is between the different photo receivers that are built. And then are there things like temperature effects that are going to change this in a significant way? And so I think we have to decide, what's the maximum allowable variation in these delays, and then decide if we're stable at that level given the thermal environment that these detectors will be in.
Okay, makes sense. The second part was that you said if you introduce more calibration tones for your TDI tone assisted TDI arranging, that you would be able to disentangle common mode and differential delays. I was wondering, is that actually needed to disentangle these two components to do the laser noise suppression? Because in the end, you apply one delay to each time series, and
right.
Do you need
do
you need to know what is common mode, what is not common mode, because you delay each time series once? So I would think that it's enough to know the total delay that you need.
I think it's to do with so you're saying like in TDI, you're already delaying these time series. And so really you're suggesting that maybe you can just like treat all delays as like a single delay and just correct for that. And you're measuring that with the tones. Is that what you're suggesting?
Yes.
Yeah, so I guess from our understanding, like the fact that they have this different frequency response, TDI has a different frequency response to these tones, to these delays, whether they're the differential or common mode ones. We think that means that treating them as a single delay doesn't necessarily correct for them. Like our analysis suggests they really do need to be like treated separately.
Okay, interesting.
But yeah, that's something we really want to study, and I think Martin's results have been really good. So hopefully building from there isn't too difficult.
Okay, thanks.
Well posed questions. Thanks, Olaf. And I think we should formally conclude the last data analysis session. I think we exhausted the TDI data analysis pretty well in this session. So I want to thank Quentin, Martina, Olaf, and Martin, Sam, and Mario for this session and making it lively and engaging with the recent developments in TDI. So with that, we conclude the session formally. So if you're hungry like me, go get dinner before, or food before the plenary starts at 8 CEST. Otherwise, I think we can leave the room open for further discussion if you want. So what do I need to do, Alistair?
That's everything. That's lovely. Thank you, Sveta, for